Okay, I think we are live. Hello, everyone. I'll just briefly introduce our speaker for this session. Dr. Snehanshu Saha holds a master's degree in mathematical and computational sciences from Clemson University and PhD from the Department of Applied Mathematics at the University of Texas at Arlington. After working briefly at his alma mater, he moved to the University of Texas, El Paso as a full-time faculty in the Department of Mathematical Sciences. Currently, he's a professor of computer science and engineering at PES University and heads the Center for Astroinformatics, Modeling, and Simulation. He is also an associate professor at AppCare, BITS Pilani, Goa, and a visiting professor at the Department of Statistics, University of Georgia. Dr. Saha is a IEEE senior member and ACM senior member, among other positions in prestigious academic associations. He is a recipient of the Peace Award for his foundational contributions to machine learning and astroinformatics. Dr. Saha's research interests lie in data science, astronomy, and theory of machine learning. So, Professor Saha, thanks for being part of this event.
Thank you, Ed. Thank you very much for inviting me. And I'm quite impressed at the way the symposium is going, and especially with the kind of enthusiasm that we see, 3,000 plus participants. So the topic of my talk today, from the title, it may sound a bit generic, from small data to big data, the evolution of artificial intelligence techniques. But what I would try to focus is the change in the landscape from small data inferences to big data due to the volume, velocity, and veracity of large chunks of data. The idea is it too difficult for comprehension in the sense that in the technicalities of processing such large amount of data with the limited computational and other infrastructures and human cognition that we are currently endowed with, are we willing to sacrifice the elegance that has had at least 50 years of contribution in small data inferencing? Okay. So I will talk both about pattern recognition in small data as well as the pattern recognition in big data, particularly which is currently driven by advances in sophisticated deep learning techniques. In between, I will intersect with some of the contributions of some masterful minds in pattern recognition and machine learning, not because I want to talk about what they contributed, because we probably know what their contributions are, but the sort of diversity and interdisciplinarity that they brought into this particular area. Okay, I mean, there are fantastic talks yesterday and a really lovely talk by Lavkesh, before lunch. And when I look at the questions that people ask after the talk, is that some of the questions are related to the topic and the title of the talk, and some of the questions are aimed at sort of career questions in machine learning, right? So having observed that, I have inserted a few slides on that as well. I'm not going to talk about those, but I mean, just for completeness, because I understand eventually when the symposium is over, these slides will be shared among the participants. So for that purpose, I inserted a few of the slides. The central point that I'm going to try to drive in today is that the elegance of statistical and mathematical inferences, so crucial for pattern recognition problems, cannot be ignored, whether it is small data or big data. And along the way, there would be a mild critique of deep learning in big data, and a very nice scenario, nice and welcome scenario that I have observed in the last 2 to 3 years in deep learning and big data research is that those methodological elegance is re-emerging. So I'm going to talk about that. Now, when I was contacted by H, I mean, he requested me to talk about machine learning, astronomy, and scientometrics, and my response was it's sort of difficult to fit in all these three in one single talk. However, I mean, what I have tried to do is, at least talk about one example from astronomy and how, big machine learning techniques are, playing a crucial role in big data inferencing in astronomy. All right. Okay. So with this, let's begin. So we know I mean, essentially data science, not really big data. It has several applications: healthcare, business, autonomous vehicles, computer vision, credit card fraud, anomaly detection, so on and so forth, right? I mean, but I just, because I want to start from small data pattern recognition, I will focus on a very particular problem in customer segmentation, and I will give an example from India. So after independence, when the public banking model was put in place by the policymakers, they sort of gave a mandate to State Bank of India to try to penetrate as deep into rural India as possible, right? And then so when the State Bank of India authorities were mulling how to penetrate the customers and how to tap into the customers in several parts of the country, and even now communication to several parts of the country remains a challenge. You can imagine what it was, I mean, right after we achieved independence, right? So they wanted to do some sort of a customer segmentation, and they were thinking how they would do it. Okay. Fortunately for them, there was something that was already done about a decade earlier by, I'm just going to skip to this slide, I'll come back to this, by whom I consider India's first, and in my humble opinion, India's finest data scientist, Professor P.C. Mahalanobis. Okay. I mean, among his several other contributions, he is known and remembered for his Mahalanobis distance. Now we know what a Euclidean distance is, right? I mean, an Euclidean distance is just a distance between 2 points separated in space, correct? I mean, as long as the dimensions of the points, I mean, as the dimensions of the data are not, correlated, as long as they are equally weighted, this Euclidean distance works fine. Because one of the principal problems of Euclidean distance is that, it's not a distance between a point and a distribution. It's just a distance between 2 data points. Now, back to the customer segmentation problem. Now, imagine you have what you are trying to do. You are a retailer, and what you are trying to do is you're trying to group people in small clusters, right? I mean, and why do you want to do that? I mean, one of the reasons why you would want to do that is, suppose you have observed there are some similarities in the pattern of spending among certain groups of people, and you club them together. And let's say you have a cluster of 300 people, and among 300 people, you observe that about 220 people are buying one sort of jeans. They're just, I mean, they have bought one sort of product, right? So what you can do, that's your queue. You can take that queue and suggest to the remaining guys in that particular cluster that, well, you may like this product, right? Okay, from a business point of view. Now, in order to do that, what you need to do is you need to be able to group people together, I mean, based on several things, not only one attribute, but several attributes, right? And therefore, what you need to do is that you have several points. I mean, you can think of each customer as a point distributed in space, and it is definitely more than 2 dimensions because of the several attributes. And you would want to compute whether certain data points are within a cluster, meaning they're tightly tied to each other, and then there are certain points which belong to another cluster. So essentially, the distance that you are computing are distances between points in a cluster, and also the distance between the clusters, right? Essentially, the distance between the distributions. This is where Euclidean distance sort of fails and leads to misleading information for 2 reasons. One is that many a time the data is not scaled. Let me give an example. Let's say you have some property data. I mean, you have area of an apartment in square feet and followed by its price, right? And in that same data set, you also have area of some apartments, not in terms of square feet, but in terms of acres. Now, when you change this unit, what will happen typically is that you will see a drastic difference between the values. I mean, if you just look at the values and based on the values alone, you try to compute the distances between these points and you rely on Euclidean distance, you are very likely going to draw false or misleading inferences because of the change in scale, right? Okay. There is another problem which is called a correlation dimension. I'll come to that later. But this, well, I mean, at least this problem you can solve by scaling it by using a Z normalization kind of a thing. But this correlation dimension cannot be solved using Z type of normalization. Why? Because what is a correlation dimension? It may so happen that among the several attributes that you are looking at, some attributes are strongly correlated and some attributes are weakly correlated statistically, right? And so therefore, if you do not factor that in, what you could actually have guys clubbed in a wrong cluster, okay? All right, so this is where PC Mahalanobis comes in with his, intervention of the Euclidean distance. Intervention of the Euclidean distance, and he calls it Mahalanobis distance, which is essentially a multivariate equivalent of the Euclidean distance. Okay, so what it essentially does, it solves both the scaling problem as well as the correlation dimension problem. So what it does is it transforms the columns into uncorrelated variables, scale the columns to make their variance equal to 1, and finally it computes an Euclidean distance. So if you really look at the representation here, you will see there is a term on the left and there are 3 terms on the right. Okay, so what really happens is, X is the vector of the observations and M is the vector of the mean values of independent variables, which is the mean of each column, right? And then there is a covariance matrix. Okay, so what you are essentially doing, this covariance matrix plays a pretty important role. So what is X minus M? X minus M is nothing but the distance of the vector from the mean. And then the way this formula is devised, we divide this by the covariance matrix or multiply by the inverse. Now, what is the purpose of doing this? If you do this, what happens is if the variables in your data set are strongly correlated, then the covariance will be high. Dividing by a large covariance will effectively reduce the distance. On the other hand, if the attributes are not correlated, then the covariance is not high and the distance is not reduced much. So therefore, it addresses both the problems of scale as well as the correlation of the variables. Now, why I invoke this? Because strangely enough, I do not see, much applications of Mahalanobis distance in clustering, which is an unsupervised, machine learning technique. Okay, I really don't know why. But it's really, really helpful. Okay, and take a pause for a moment and imagine the brilliance. It's a simple solution, but it really solves a lot of problems in which we encounter, we try to solve in real world data sets. So back to State Bank of India, when State Bank of India tried to figure out how they are going to do this market segmentation, okay, they actually went back and used this Mahalanobis distance. And Mahalanobis was fortunately part of the first planning commission that India set up after independence as well. Okay, so now, can this be used when you have a huge amount of data? And we know in big data, in particularly 1 minute, it's multimodal in nature. It's a lot of data, okay? And the one of the things of big data is, probably as Professor Michael Jordan of UC Berkeley put, that you probably experience an epidemic of false positives coming out of big data projects. Why so? Imagine you have large amounts of data as depicted in the picture, right? And therefore what happens is your appetite for hypothesis tends to get even larger. And if it's growing faster than the statistical strength of the data, then many of your inferences are likely to be false. In a classical database, what happened? You have maybe 1,000 people, right? And you have some columns which are the attributes or features, right? Now, what happens in a big data landscape is that the number of combinations of these columns grows exponentially with the number of columns. So if you have many, many columns, and that's what we do in modern databases, you will get up to millions and millions of attributes for each person. Now, if you start allowing yourself to look at all of the combinations of these features, like for example, let's say you live in Goa and you ride a bike to work and you work in a certain job and you are of a certain age, then what's the probability that you will have a certain disease or you will like my advertisement? There is an ad and you're going to like it. Now, what happens is you are going to get millions of attributes and the number of such combinations is exponential. It gets to the size of the number of atoms in the universe, really. Okay. So these are the hypotheses that we should be willing to consider. And for any particular database, we can find some combination of columns that will predict perfectly any outcome just by chance alone. So if I just look at people, all the people who have a heart attack, and compare them to all the people that don't have a heart attack, and I'm looking for combinations of the columns that predicts heart attacks, I'll find all kinds of spurious combinations of columns because there are huge numbers of them. Okay, and once again, as very eloquently put by Professor Michael Jordan, it's like having billions of monkeys typing simultaneously, and perhaps one of them will write Shakespeare. Okay, all right. So having said that, it's not all bad. So there is this one example from astronomy where in the last 10 years, particularly in the last 5 years, thankfully to the advancement of both Russian and Chinese space missions along with NASA, we have an huge amount of data. Okay, particularly the Galaxy Evolution Explorer, which was spearheaded by the Sloan Digital Sky Survey at MIT, and then the LSST survey. So the scale of the data ranges from terabytes to petabytes and up to exabytes. I mean, what we are expecting is by 2022, when the Chinese space mission completes, it's going to generate exabytes, 30 to 35 exabytes of data. Okay, all right. This particular data set is just objects that we observe. What kind of objects? Galactic and extragalactic ones. So stars, galaxies, and quasars. So far, we have about 1.5 billion stars, galaxies, and quasars that are observed and cataloged. Okay. Now, the question is, when I try to classify, and a lot of these objects need to be classified. When I try to figure out an automated classification scheme, is it a big data problem, or there are things that perfectly work in the small data domain that can be imported here? Okay, so turns out what could happen is, out of these 1.5 billion objects of stars, galaxies, and quasars, and believe me when I say this, there are only 47 objects which are stars and quasars, which are extremely hard to classify. Rest are not. Rest are quite easy to classify. I mean, you can use any of your deep learning methods or neural network based methods, whatever you use. So out of these 1.5 billion objects, only 47 are problematic. Okay. So the question is, I mean, do I really bother about going about an architecture which is expensive both by hardware and as also by algorithm, or I really focus on the tiny data set, a tiny subset of the data that is difficult to classify? Okay, so there are strategies that at the interplay. I mean, we some sort of migrate some of these strategies that we employ in small data, okay, and sort of divide the data by drawing knowledge from the domain and solve such problems. So this is what I mean by porting small data pattern recognition to big data pattern recognition. Okay, all right. So the question that I pose is the over-reliance on deep learning architecture that we have seen in the last 10 to 12 years absolutely necessary? I don't think so. And the second question is that all the elegance that we have spent at least 50 years on, starting with the evolution of learning theory, statistical learning theory, is all the elegance lost? I don't think so. Okay, all right. So and then there are, see, whenever you talk about big data, if you really think, if there is a one-dimensional pitching of what big data can do for you, you should also be in a position to tolerate, such sort of jokes and sarcasm that should come your way. Okay, all right. So when I say deep neural networks leading to false meaningless inferences, once again, going back to that same star quasar galaxy example, most of these objects, it also depends on what kind of features you would use. Now, there is one particular feature, it's called the redshift. Okay, now if you use that particular feature, the machine learning problem becomes trivial. Okay, because most of these objects, stars, galaxies, and quasars are perfectly linearly separable across the redshift. So if you're using redshift, there is not much to train your model on. And if you report like 99.6% accuracy by, first talking about a very fancy deep learning architecture, at the end, what you are inferencing is something that is, subject to harsh criticism. And this has been the case. Okay, there are a couple of work, and one of this particular method was to be deployed almost by one of these space agencies until someone called the bluff, and the model was, taken off. Okay. Now, this is just the cost. I mean, to set up a modest cluster computing setup to do what kind of the kind of big data inferencing and prediction that you want to do would cost you about, on the upper side, anywhere between 80 lakhs to 1 crore, and on a moderate side between 40 to 45 lakhs. Okay, all right. This is because, I mean, we rely on artificial neural network architectures. Okay, all right. I mean, I'm pretty sure you have heard of it. And you know that it's just an interconnection of layers, input layers, neurons in the input layer, neurons in the hidden layer, and neurons in the output layer. There are thousands of weight combinations, technically thousands of neurons, right? So it's become thousands of weight updates. So it's an expensive process. Okay, the reason we tolerate such expensive process is because what happens is, one of the good things about artificial neural network methods is that it handles nonlinearity quite well. Okay, now most things about most of these methods that deep learning has brought about are not bad. In fact, most of them are good. So the good ones are, I mean, there have been several methods that have been proposed in the past and are successfully employed for a variety of reasoning and inferencing. There are fantastic architectures that came about. Okay, and because we had to effectively figure out or test our methods, there have been huge data sets which could actually challenge your deep learning algorithms, right? And some nice tools in big data also came out. Okay. Well, one of the concerns that we have is at the training time. Okay. So there is this recent, technology review in MIT Technology Review by Karen Howe, where she reported that there has been a study by a research group at University of Massachusetts Amherst, if I recall correctly, and they tested. I mean, they're trying to evaluate the carbon footprint of state-of-the-art NLP models. And what they really figured out after all of the experimentation is that your carbon footprint that your training model is costing you, the carbon emissions, is actually equivalent to 5 American cars. Imagine that. Okay, now the question is, do I bother? I think we should, right? I mean, so far we haven't, but I think it's time that we take stock of what cost we are achieving this sort of predictive power. Okay, now the ugly part. Now I don't know whether probably some of you are aware. I mean, there is a paper and technical report. This is uploaded on arXiv by a couple of researchers from University College Dublin on July 1st this year, and they pointed out several inferences coming out of the MIT tiny image dataset. I mean, they call it a tiny image dataset. This dataset is embedded with lots of metadata and levels. Okay, and the prediction is, laden with racial slurs, misogynist slurs, and a lot of other nasty things that needs to be avoided at any cost. Okay. Now, the response from MIT was that we did not know, we were not aware of the levels in the image data sets, and we did not realize the implications of it, which I think is bollocks. But anyway, they apologized formally and pulled off this huge data set, and this particular data set has hundreds and thousands of citations, and people used it. Okay, all right. So imagine now. So as I said, I mean, see, I'm not here to critique the architectures or the methods or the standard modus operandi of how we are going about big data inferencing. But what I'm trying to say is that along the way, it would be a cardinal mistake if we ignore some of the things that we have learned in the last 50 years. And this is where Professor Vladimir Vapnik, comes in. And look at the timeline of this guy. He has started something back in 1964 from a generalized portrait model, which he was trying to figure out OCR, character recognition, optical character recognition. And when he was done with what he wanted to do, it took him like at least 1992 is slightly wrong. If I include the kernel, then it is actually 1995. Okay, all right. But during this time, we also observed an implosion of algorithms, methods based on mathematical proofs in statistical learning theory. Okay, all right. And when Vapnik was done with his support vector machine for non-linearly separable data in 1995, we could say that one cycle was completed. Okay. Now, in the last bullet item, you see a masterclass 1903. What do I mean by that? This masterclass of 1903 is due to a gentleman known as Mercer. Okay, and just below his image, you also see another gentleman whom everybody, I think, beyond reasonable doubt, considers him as the father of the modern advanced functional spaces, based on which a lot of your deep learning methods are, driven by. Okay, so the reason why I bring up Kernel and Hilbert together is because a few slides back, I talked about a problem of galactic and extragalactic object classification, right? And there I mentioned that it's a huge data set, but in that huge data set, there are only a few data points which are problematic. Okay, and what do I mean by that? I mean that most of the data points in that particular data set could be separated by something like this, which you can see not just one line, you could actually see a margin, right? And this is the essence of the support vector machine or SVM classifier, that what Vapnik proposed is as essentially what you are trying to do, you're trying to classify two different classes, right? Two different sets of data points which should belong to two different classes. And this classification problem is eventually translated to an optimization problem. Okay, so which is the point of what I do? I believe that optimization is at the heart of machine learning, both traditional machine learning as well as deep learning problems, right? However, those 47 data points that I was talking about could not be separated by this kind of large margin classifiers. Okay, one thing, you can forget the math, you can completely ignore the math, but just note for a moment that there are a lot of inner product computations when Vapnik actually came up with your support vector machine classifier, right? And it is in the context of these inner product computations that we went back, we meaning me and the students that I worked on this, have been working on this particular problem, and we see this. So these are just, the falsely classified objects, which are stars and quasars alone. So what really happens is, because of photometric emissions, some stars become too hot, and when they become hot, the photometric magnitudes which we use as the features for the eventual machine classification problem, the photometric magnitudes become really, really close to the one that of the quasars. And so therefore, in a 2D space, you are not able to use a support vector machine like argument or a linear separability kind of an argument to separate out the stars from the quasars. Okay, all right. So if you continue with what you have been doing, which is the any of the other methods, right? You would actually end up with a lot of false positives and false negatives. So here comes the trio. That's why I mentioned that 1903 masterclass, the Hilbert, Mercer, and Vapnik. So what they have done together, of course, Mercer passed away by that time, but the Mercer's idea of a kernel is essentially a higher dimensional embedding from a lower dimensional space. Okay, So Vapnik used it beautifully because he was already doing a lot of inner product computations when he devised his classifier. So, and essentially the idea of a Hilbert space, which is a complete infinite dimensional vector space, okay, with an inner product defined on it, right? Okay, so theoretically speaking, when he proposed the kernel, when the kernel was proposed, the idea was if you cannot separate out the data points in a lower dimensional case, you use an infinite dimensional embedding, theoretically speaking. For all practical purposes, what it means is that the dimension of the output space would be extremely large, right? But since theoretically it is infinite dimensional embedding, you could draw all the results on the inner products that already existed in the Hilbert space and also defined by Mercer. Now, what Mercer did was, in order that an inner product becomes a kernel, in order that an inner product kernel is defined, he listed 4 properties. And there is this theorem that he proposed. And he said that in order to be able to effectively define an infinite dimensional mapping, you need to satisfy all these 4 properties. And this is where the beauty of a beautiful mind is that, if you're able to do that, your original formulation in the inner product is transformed to a formulation in terms of the inner products of the kernels. Okay, but all the 4 properties that Mercer initially defined are actually not required to show that it is a kernel that you need to use for this particular classification. Because out of those 4 properties, the last 2 properties are, you can have a linear sum, right? Just an additivity of 2 inner products. And the 4th property was, you have an orthogonality property, which means if you have 2 training examples, they are orthogonal to each other, and the inner product eventually is 0. Now, when we do a nonlinear classification problem, so this is the visualization of a kernel embedding, right? You can see what you cannot separate out in 2 dimensions by using a linear separability or a hyperplane. You can essentially do it by this kernel embedding, right? Now, what kind of kernel? I'm not at liberty to say, but I'll say this, that when he was using Mercer's conditions for his particular kernel method, he argued effectively and correctly that the last 2 properties are not needed. Because since a kernel is a nonlinear embedding, it makes no sense to satisfy the additivity of the linear property. And also there is no necessity that your training examples pairwise are orthogonal to each other. Okay, so this is the beauty of it. You use something, but you modify it accordingly, right? Now, back to the problem that we were trying to solve, that is those 47 data points of stars and quasars. So here we actually went one step back and looked at what economists, econometricians view, what is their view on kernels. I'm a little surprised to find out from the literature, and I've spoken to some econometricians myself, is that this kernel approach in economics is not a very popular one. Not a lot of people use it. But the interpretation of kernels by economists is slightly different. What they see is that, let's say you define a kernel, and typically a kernel has parameters or hyperparameters that you need to tune, right? When you define a kernel, what they would like to see is that if the parameter values are tweaked, if you are increasing the value of the parameter, it should essentially minimize your risk in prediction. That's the way they interpret it, which means, I can definitely talk about some of the established kernels, like for example, in the Gaussian kernel or in a polynomial kernel. Particularly in a polynomial kernel, there is an exponent involved. So what they're trying to say is that if you try to increase the power, if you try to increase the value of the exponent, your risk will be minimized, or at least it shouldn't get worse. Now, those who are familiar with this kernel experimentation knows that this particular parameter part of kernel experimentation is sort of a black box. Okay, we really don't know whether the error bounds become progressively tighter for example, when we apply a polynomial kernel, if we increase the exponent, we don't know that. There has been no theoretical determination during this regard. This is where we thought, I mean, if something from economics can be imported, I mean, and production function and utility function that econometricians use, and if we can prove that this works as a kernel as well. Essentially, what all we had to do was to prove the two properties of a Mercer kernel. The first property being it has to be symmetric, and the second property being it has to be positive definite. If we are able to show that these two properties hold, then by leveraging that production function from economics, we can argue that there is this parameter that we are using, and both theoretically and experimentally, we can show that if I increase the value of that parameter, then the error margins get progressively tighter, and there is empirical evidence of the same. So far, what we have been able to successfully do is that we have solved this nonlinear separability problem of stars and quasars, which is why I said that why should I bother about the rest of the large numbers of stars, galaxies, and quasars when I can use any method practically to effectively separate them. I would rather focus on this small segment of that data, right? And using this particular kernel inspired from economics, we were able to do that. And we were also able to show, at least empirically till now, that if I fiddle around with that particular parameter in the kernel, the error bounds, or the in this particular case, since it's only the practical experimentation stage for now, the accuracy is sort of increasing. Okay, so far so good. Okay, so so I mean there should be a comic relief in between. So this is one of my former student who is trying right now is trying to train his deep learning model, and you can see this is a refrigerator, right? Okay. So his laptop was getting very hot, so he just kept his laptop there so that it just doesn't blow up or smoke doesn't come out or something like that. I mean, ironically, this is the guy who actually worked with me for the kind of computations that I always advocate, which I call parsimony computing. I mean, his considerations during his PhD, probably his priorities have changed, so he has gone back to just using off-the-shelf deep learning models. That's okay. All right. So the idea is parsimony computing, right? Which is optimize, optimize, optimize. Try to come up with new methods in optimization, right? So that your prediction error is as minimum as possible. Try to get rid of expensive architectures, which I mean like typically, essentially, if I'm able to solve a problem by using a shallower architecture, shallower neural network architecture, why would I rely on a deep learning architecture, a really deep architecture, right? Okay. And also there is this thing about single shot learning, but I really don't have the time to talk about it. Now, some of these things that you see in some of these slides are actually in response to some of the questions that I heard yesterday, right? Okay, so I'm not going to talk about what you need to become a machine learning expert or something. So, but the considerations are the following. Yes, accuracy, you increase the accuracy, minimize the loss. That's sort of obvious. But I mean, can we try to see if the number of epochs that we require to converge to an optima can also be reduced? Okay, can we also try to see if the CPU and memory utilization are kept to a minimum? Can we also try to see what is the implication? I mean, what kind of carbon emissions are your algorithms, producing? Okay, and obviously there are certain things that we should avoid, like that MIT tiny image data set. I mean, predictions that have like that are clearly violate all ethical, social, and racial norms. Avoid some ridiculous mistakes like using redshifts for inference, which makes no sense, right? Okay. So the devil is always in the details. It's one thing to talk about coming up with efficient methods, but there are, I mean, as far as a neural network is considered, what is an efficient method? I mean, there is a parameter, there's a hyperparameter, which is in a gradient descent learning that you need to tune, right? Okay, and that is the learning rate. How are you going to tune it? And there are several, even you'll see there are several papers to that effect. Okay, all right. But what we tried to do was something very simple. What we tried to do is that we looked at the loss functions and not at the activation functions. So when we looked at the loss functions, we saw what kind of loss functions are typically used in a neural network. You use mean square error, you use binary cross entropy, you use cross entropy, and you don't really use mean absolute error much, for the simple reason that the mean absolute error has a point of discontinuity, has a point of non-differentiability in the domain of it, right? Okay, but let's say for a moment that yes, I mean you can use mean absolute error as a loss function as well. Then what sort of learning rate that you could automatically set so that it does not have to be tuned in the subsequent epochs? So it turns out what we did was we set the learning rate as the inverse of a Lipschitz constant. Okay, and if we do that, we are sort of forcing the weight changes to be constrained between 0 and 1. Under the fairly weak assumption that gradients in a deep neural network under backpropagation do not change arbitrarily fast. Okay, now this condition is really weak. Now, I don't know whether you know what a Lipschitz constant is or what a Lipschitz function is, but I mean, let me tell you that what it is that a Lipschitz continuous function is limited in how fast it can change. Okay, and so there could be a constant, or just a real number, okay, that for every pair of points in the graph of a function, the absolute value of the slope of the line connecting the two is not greater than this particular real number. And we call this the Lipschitz constant. And the smallest such bound is known as the Lipschitz constant. Now, how is this relevant in neural network training? Because in a neural network training, you know that gradients are smaller than in the earlier layers than in the last layer, right? And therefore, what we can do is we can turn this inequality around to our advantage. And we note that at every layer, the gradients could be bounded by this Lipschitz constant, right? And as you progress from one layer to the next layer, your Lipschitz constant changes. As your Lipschitz constant changes, your learning rate automatically changes because you have set it like that in your algorithm, right? So, I mean, I tried very hard to insert a visualization of a Lipschitz constant in the Beamer presentation. I couldn't. So I'll just go back to the local drive, and I hope you can see this. I hope you can see this, right? So what you see is that there are two white cones. Okay, so you move these two white cones at the origin in such a manner that your Lipschitz function, which is a blue line, okay, just continues as a tangent, but it is like always stays outside the cones. This is the geometric interpretation of a Lipschitz constant. All right. So if I go back, but then the question is, other than this, easily observed empirical understanding that if you set the Lipschitz constant as, I mean, learning rate as the 1 over Lipschitz constant, your weights are constrained, but so what? I mean, typically, what I just described about a Lipschitz constant can be mathematically represented like this. Now, if you hold your thought for a moment and think about what you learned in high school and first year college, you know that you have learned something called mean value theorem, right? And what a mean value theorem says is that if there is a continuous function, and which is defined on a closed and bounded interval, then, and if that continuous function has just the first order derivative, then, I mean, by mean value theorem, you can argue that this first order derivative can be bounded. And this is actually the Lipschitz constant. So when you are assuming that your loss function is Lipschitz continuous, you are only assuming that the first order derivative of your loss function exists. And that is the case in mean square error as well as cross entropy. And we have shown in a separate work that if you take care of the point of discontinuity and point of non-differentiability in a mean absolute error by doing an epsilon smoothing, you can actually extend this Lipschitz continuity idea and compute the learning rates for mean absolute errors as well. Okay, all right. So the assumptions are minimal. You are not really making any assumptions about the Hessian. You are not really making any assumptions about the second order derivative of the loss function and so on and so forth, right? And obviously, the obvious question that pops up is this supported by the experimental results? The answer is yes. Is this supported across different architectures? The answer is yes, right? Okay. Now, typically, you know that in gradient descent, you apply the chain rule, right? Okay. And then from the chain rule, based on any loss function, the commonly used loss functions that you use, I mean, if you apply it to a regression with neural networks problem or even with a classification problem, you should be able to derive the learning rate. And it turns out that for the regression problem, the learning rate is what it is on your screen. For binary cross entropy and multi-class classification, softmax regression loss, you can figure out the learning rates. Okay. Here, X is the input data matrix, and K is a constant, and M is the number of training examples. Okay. All right. Now, there could be a deeper question thrown at us. I mean, why such choice of a learning rate? So what we have been able to show is that if we choose such a learning rate, I mean, we can show that the gradient descent has like a convex quadratic upper bound, which can be minimized. Okay. If the learning rate is set at 1 over L, and as long as the learning rate is less than 2 over L, the method works and the gradient in the successive layers decreases, right? And we have also shown that if there is an error tolerance that we set a priori, in order to achieve the error tolerance, you need at least a certain number of iterations of the order of 1 over epsilon to achieve the error bound. So it will converge. Theoretically also, it does converge. Okay. All right. So these results are important because it then shows that, you know, if you set a learning rate like this in your learning discipline, then there are theoretical guarantees that your algorithm will converge. Okay. I mean, how do we prove this is using the mean value theorem again and some telescoping some ideas and other. For a complete proof, you can always refer to the paper, right? So this idea of loss functions is agnostic of the kind of activations that we used. This works on sigmoid, ReLU, or whatever other. It's also independent of our architectures. However, a standard question that you would always have to encounter is that, is the architecture, I mean, have you applied this on really deep architectures like ResNet 18, ResNet 20, you know, DenseNet 40? The answer is yes. Okay. So what we really wanted to do was that we wanted to reduce the number of epochs to converge to the same benchmark accuracies of the other state-of-the-art optimizers. And yes, we have achieved that, right? And we have also compared the CPU and the memory utilization of this particular method. And it turns out that these are better compared to the other state-of-the-art optimizers. Okay. So what I mean by parsimony computing is that we would like to progress in terms of parameter handling. We would like to progress from tuning to an automatic selection. Okay. All right. So therefore, I mean, as you can see, along the way, there are several other things that I would like to talk about, but I think I'm running out of time. And I have listed some old and recent papers from both, traditional machine learning as well as the more new deep learning methods. And some of these papers are actually talk about why a deep learning architecture, under what circumstances a deeper network works better than a shallower network, and so on and so forth. Okay, all right. And there are, I mean, these are slides which will actually answer some of your other questions, like which courses should you take, which books you should read, right, and so on and so forth. Okay, so I think probably it's a good time to stop.
Yes, thank you for your very interesting talk. A
Open to
lot of
questions.
interesting examples that you gave also, which were very helpful. So I think we have time for about 2-3 questions. So we can do a short Q&A. So I'll just ask you, so can you hear me?
Hello.
Can you hear me? So are you able to hear me? Okay, so we can start with the first question. When we talk about astronomy, shouldn't our focus be on small architectures with minimum latency to get live results instead of worrying about the costs of data transfer?
Yeah, my headphone suddenly has stopped working, but I can hear you now. I'm looking at the question. Yes, that's precisely what I said eventually, right? Uh, Not only on smaller architectures. I mean, you derive, you use the domain knowledge and figure out which subset of your data that you are facing the most difficulty to infer. It turns out, as I said, as I explained, right, there are like about 47 data points which are really hard to classify, and what we did to classify that.
Right. Okay. Another question is, since it's hard to procure data in the context of astronomy, is zero-shot learning or one-shot learning, do you think it has a future in this field?
Yes, I'm glad you asked this question. But when you say like a few shot learning, you essentially have to be able to exploit the chaotic nature of how the neurons behave, right? So you bring in components of chaos theory like GLS neurons, and there is a translation entropy map and things like that. In fact, we do work in that domain as well. But I prefer not to talk about it. But the answer is yes. So use the techniques on a smaller fraction of data and try to port it to a larger fraction. Yes, that is the way to go. In fact, this year's NIPS 2020, there is a paper. I don't remember the name of the authors, but there is a paper on this particular, chaotic learning paradigm, which is like one shot or a few shot learning.
Okay.
The question number 4, with the arrival of quantum computing and machine learning, do you think it will be next important breakthrough in big data analytics? I don't know enough about quantum mechanics to begin with to answer your question. What I know is the phenomena of quantum tunneling that physicists use all the time, that could be leveraged to solve some of the local minima problems that we face in deep learning architectures. I know that much, but I don't know beyond that.
Okay. And there's another question. With the recent GPT-3 language model, there has been a debate on if just procuring more data and building larger models is enough to improve performance, or if we need to improve our learning algorithms as well.
No, I think, my talk if you look at the entire talk, right? I think I have answered this, at least, even if I haven't answered this question, I pretty much told you what my take on this, right? I do not think that over reliance on architectures is the solution. And I think that you need to, devise really elegant methods. Like I can give you example of one paper where they have shown that if your loss function is Holder continuous, which is actually basically a functional embedding of Lipschitz continuous functions. If your loss functions are alpha Holder continuous, then your deep learning architecture, and a typical deep learning architecture, if you increase the number of layers, you actually theoretically obtain a tighter error bound, right? But there is no guarantee that such alpha Holder continuity property holds for all loss functions. So I think the idea is, in general, the idea is, we focus on the loss functions. That's one thing. We also focus on the activation functions. I did not have the time to talk about the activation functions. In fact, some of the activation functions can be derived from the same Lipschitz criteria. By the way, the Lipschitz constant that I was talking about, if you constrain that value of the Lipschitz constant between 0 and 1, you actually get a contraction mapping. And if you get a contraction mapping, you can actually think of Picard-Lindelof type first order differential equations whose solutions can be your activation functions. And that has some implications towards your neural network learning as well. Okay,
interesting. So I think we are out of time.
Okay.
So thank you, sir, for your great talk and being part of our event.
Thank you.
We'll move on to the next session in about 5 minutes. So everyone who's watching, please stay tuned.